Hello and welcome to this stationary waves paper 1 worked example, just what you've been waiting for. A transmitter of electromagnetic waves is placed 45 centimeters from a reflective surface. The emitted waves have a frequency of 1.00 gigahertz. A stationary wave is produced with a node at the transmitter and a node at the surface. And the question that we want to solve, how many antinodes are in the space between the transmitter and the surface? 1, 2, 3, or 4. Let's jump over to the chalkboard. This transmitter looks a lot like a speaker, but it says that it's an electromagnetic wave, so it's creating pulses of light. And light always goes at one speed, speed of light, c. And so that speed is 300 million meters per second, or 3 by 10 to the 8 meters per second. Given the frequency and knowing the speed, we could calculate the wavelength, and that's certainly something that we're going to want to do here. So the speed of light is equal to wavelength times frequency. We'll plug in this value for speed. This value will convert into hertz instead of gigahertz, and we'll solve for the wavelength here. And so I'm going to rewrite this over here as the wavelength equal to the speed of light divided by the frequency. Speed of light is a constant 3 by 10 to the 8 meters per second. The frequency is 1 gigahertz. Hertz is the same thing as reciprocal seconds, and so we'll cancel those units out. We'll be in meters. 3 over 1 is 3. 10 to the 8, so minus 9. So we just got like 3 by 10 to the negative 1, which would be 0.3, right? But double check that in your calculator. You're allowed to use a calculator. So we have a wavelength of 0.3 meters or 30 centimeters. We're given the distance between our transmitter and the reflective surface, 45 centimeters, and an entire waveform is going to be 30 centimeters. So kind of imagine like breaking this up to like 15s, like 15, 30, 45, right? So and 30 of these is going to be an entire wavelength. And so we kind of imagine like there's a node here, they told us that. So a node from node to node is half a wave, right? So we go here to here is half a wave. And we have our entire wave occupying 30 centimeters. And so there's half a wave. So there's our wavelength, 30 centimeters. And then we have another half a wave here. So we can visualize sort of the standing wave like that, right? The question asks how many antinodes. And once you visualize the waveform like this, the question told us there was a node here and a node here. You have to use the wavelength to sort of, sketch that out. So if this is 45, then an entire wave is going to occupy sort of that much 30, and you get another half a wavelength there. The other thing you can do is take this number and divide it by the wavelength, and then you'll see, it's 45 or 0.45 divided by 0.3. You say, oh, I've got 1.5 waves that fit in this space here. The question about the antinodes is you can just sort of read off now. There's an antinode 1, 2, 3, right? Each of these places with maximum displacement is going to be an antinode. So the correct answer to this question is C. 3. Considering the answer choices below, definitely choice C. This has been another worked example with Dr. Schleith. See you next time.